Morning, everyone. Only a couple of you here so far. Let me know if you have any questions. We got about 4 minutes before class is supposed to start. I'm just setting up my notepad thingy. No questions yet. I think I know one question somebody's going to ask. Let me turn that and check that out real quick. All right, still got about 2 more minutes. Y'all are welcome to ask me any questions if you have them. Okay. All right, well, we got less than a minute. So again, I'll ask one more time. Does anybody have any questions before we get started? We're jumping into chapter 25, and we should be able to this week, not necessarily today, but most of it will be done by today. Pretty straightforward stuff. It's mostly stuff to get you ready for doing circuits and things of that sort. So we got to, define current, we got to define resistance, the things that you've been using in lab already. So you have a little better understanding than you normally do. I'm curious to see how y'all actually like this material. I'm wondering if it was actually easier seeing it in lab first and then seeing it in lecture, or do you like it the other way? So give me an idea, send me an email or something, let me know. I'm just curious. All right, it's definitely time, and it looks like we got not too many. We got 6 of us in here, but as I said, we're going over chapter 25. Feel free to put up your chat if you want to, or post a chat if you want to ask a question, anything like that. Also, if you are curious about the final, about the midterm or the next face-to-face exam, I figured somebody asked me about that, so I would check it, and it is, I think, your lab days, if I remember correctly. Yeah, it told me you meet lab on Tuesdays, so that means your next test day would be October 31st. That's the next face-to-face test day. You're probably going to have another, maybe even 2 more online tests before then. So just to let you know. So we're going to start off today talking about chapter 25. It's called Electric Current and Resistance. And the objectives it states, which I don't normally state these, especially in the online classes, but it's sort of helpful. It's to relate electrical current to the net charge flowing through an area and associated time interval. Relate electric current density to the concentration, charge, and drift velocity of charge carriers. That's sort of towards the end of the chapter. Relate the resistivity of a material to the electric field and current density of the material. Reflect or relate the change in resistivity of a substance to the resistivity and change in temperature. Whoa. Yeah. Okay. Relate the resistance of a conductor to its resistivity, length, and cross section. Relate the voltage across a conductor to the current in the conductor and the and its resistance. That's relate terminal voltage. Relate terminal voltage of a source to its EMF, resistance, and current. So that's another one. Just let some more people in. Use relationship for power delivered to a circuit element to solve for an unknown quantity and relate the resistivity of a metal to the concentration of free electrons and the average time between collisions. I generally skip the there's a mean free path process. I usually skip that section, but we'll do the current and finding the drift velocity by modeling the elements that you'd be using our conductor as something that can give up a free electron. So we will be doing that part, but we will not be doing like the mean free path stuff, which was back in like an earlier chapter. Okay, so until Volta comes along, we have a problem, but despite that, we actually know quite a bit about electricity and magnetism by then. And I should check it out. Oh yeah, so this was late 1700s, early 1800 that Volta made the discovery or invention. Basically, he invented a battery. So before that, we had to take fur and like amber and rub them together, and that would give you a certain amount of charge, static charge, that you could then compel a nearby object that could hold the charge a little better, what we call Leyden jars and things like that, which is sort of like a capacitor. But we would go ahead and take some kind of Leyden jar and put a bunch of charge on it and then do our experiment. But basically, once you did the experiment, all the charge was gone again, nothing you could do. But luckily, before Alessandro Volta came along, and he ended up living from, I'm actually just looking up the book now that I have the picture in front of me to check the date. Volta lived from 1745 to 1827, and 1800 was when he invented the battery and showed it to Napoleon. Your book has a painting of him showing it to Napoleon in 1801. But before that was Galvani, just a couple, well, your book made a point to say it's 100 kilometers away. And in the 1780s, Luigi Galvani had reached the conclusion that he saw that frog legs would actually kick and stuff like that. He thought it might have been something about the conductivity of the material, and maybe even thought that it might have been the inner life force or the soul, something like that. But ultimately, Volta believed it was because of dissimilar metals. So Volta went to trying to experiment with dissimilar metals and made the first pile, which is what we called the battery. And it basically, you can imagine it as, let's take like a prescription bottle, a plastic little prescription bottle. Okay, let's drop a zinc washer in the bottom, and maybe let's go ahead and solder a wire to that particular zinc washer at the bottom, and then run the washer back out the top of the cup, out the top of the prescription bottle. So you got a zinc washer down there, and then what I would do is put a piece of gauze. He used something like paper or something between it and the next conductor, and he made it moist. He had it moist. It was like a salty acidic solution, and he poured that over top of the zinc and the little gauze type thing that was on there. Like I said, I could use gauze if I was given a choice. But then after the zinc, he put like a layer of, actually in his case, it was silver, but you could put another metal. You could put copper or something like that. But imagine then putting a silver washer, or at least a circular disc, and then putting another wire on top of that. And when you actually measure it with voltage, and I can't remember which one would be positive or negative with those two metals, because I just don't know the electronegativity chart by memorization. But if you did, let's say it came up to 0.4 volts, say, what basically you showed was the potential difference, the electric potential difference, which we call voltage, between the top of the silver and the bottom of the bottom zinc was about 0.4 volts. If you put another piece of paper, another piece of zinc, another piece of paper, another piece of silver, and then remove the wire from the previous silver and put it on this one, that would read about 0.8. So it basically double when you double the number of stacks of material. And then you keep doing that, you can get pretty decent voltage. So that was a really big deal, that not only could you get pretty big voltage, you could send it out at different rates and all sorts of stuff like that. So that's what Volta introduced us to with the help of Giovanni. So Giovanni, again, just seeing the muscles twitch was what gave him the idea. He published the paper, and then Volta read it, and Volta went to thinking it was the dissimilar metals. And we now know a lot of things about dissimilar metals. For instance, if you know anybody that owns a boat, you'll know that, for instance, when their boat comes out of the water, a lot of times you look and you see what used to be smooth metal have little pits in it. That's largely due to dissimilar metals under the surface of brackish water while the boat sits there. So you're more likely to see it with a boat that stays overboard all the time, as opposed to one that just a person will come and put it over on a boat ramp and then go out for the day and then pull it right back up. You don't see it as much on those, but ones that are left over, fishing boats, working boats, that sort of thing, you will get little pits. And what's going on there is basically the ionic type solution that the brackish water is. And just about any water would work as long as it's not distilled water, but you really want something slightly acidic or slightly basic, and you want it, that makes it ionic. So when you have brackish water, that's what's going to happen. And some of the atoms lose their electrons, and some of the materials actually lose whole atoms, and that's what's going on. Literally, atoms are leaving chunks of the engine when the engine has pits in it. Some of the things you can do, they'll put another dissimilar metal that is more inclined to steal atoms from the stuff that's stealing the metal from your boat engine. So you can put a little block of metal on the back and bottom of your boat, and sometimes that'll keep the lower unit of the engine from pitting so badly. So just some neat stuff like that. That's also the process that we go through in plating jewelry. So like if you take a steel chain and you want it to look pretty, you might want to coat it in silver or gold. Well, you could use a galvanic type process for that as well. So anyways, that's how we make a battery. And I wanted to just mention that to you. And now I'm going to show you an actual diagram. Now, I'm a founding board member of a facility in Elizabeth City called Port Discover. And I used to do these shows for young kids. And one of those shows I did was always making a battery. So, every year or so, or a couple times a year, we do a battery making one. And you could take literally a tomato, a potato, a lemon, an onion, a banana even, and you can go down to Lowe's and you can buy you some really thick copper wire. And then you can buy you a single really good size galvanized nail. And the copper wire is an entirely different metal, obviously, than the zinc coated nail that would be galvanized. And you stick them in opposite sides of the fruit or vegetable or whatever you use, and lo and behold, it will develop a voltage not unlike the two plates did before, 0.4 volts. And it's about that same size, around 0.1, 0.2, 0.3, something like that. And you chain them all together, and you can actually get it easily to turn on the LED. It takes a lot more time and a lot more lemons or whatever you're going to use. It takes a lot of those stacked up to actually get enough charge to go through, say, an incandescent light bulb, even those little itty bitty light bulbs like that. But that's another way you can make a battery. So let me go ahead and share my screen with you so we can start talking about the specifics. I want to show you, for instance, a battery. And actually, if you had the book, you could just look right at the drawing. They actually have a voltage drawing in your textbook, which is kind of neat all by itself. But basically, all you have to imagine is you take a bottle of some sort, some kind of container, just to contain the liquid. See, I actually consider submerging the whole liquid. That works, better for me. But you can just use the gauze and moisten the gauze between them. That'll be good as well. But now you take and you put a little washer down there, and then you put a little gauze, say, like this, and then a different metal. And if you actually took a voltmeter now at this point, and you set it to voltage, no, actually this thing's doing stupid right now, hold on. And you set it to DC voltage, okay? And then you just took and ran one of the wires, and again, electronegativity is what it's all about here, but you could run one of the wires to the bottom of the black thing, and you could run the other wire to the red thing, and it might read 0. It might read 0.20 volts, something like that. But now if you go back and put another piece of gauze, and then another piece of the, let's say this one was zinc, another piece of the zinc up there, and then you put another piece of gauze like that, and then you put another piece of the other metal, let's say that was silver, okay? Now, if you connect the wire to the top of that one, it'll read 0.40 volts. The darn thing is aggravating the crap out of me. 0.40 volts would be what happened when you doubled the stack. And you could keep on doing that. And ultimately, you could make it just about any voltage you want. You can get it clearly in the several tens of volts, and I suspect you could probably even get it to 100. I've never done it such a large amount, but that's basically what it can do. That's the idea of a battery, and that also probably makes a little sense when I tell you that the symbol for a battery in a circuit is often like this. And the long end represents the positive side, and the short end indicates the low voltage side. So that's a typical symbol for a battery. You don't have to use the 6 different plates like I did there. I've seen them with 2, I've seen them with 4. I usually see them with 2 and 4, but occasionally I even see them with 6 like this. So another symbol you might see for a battery is this. And again, this side is the positive side, and this side is the negative side. So if we're talking about, for instance, a AA battery, has its positive end where that nipple sticks out, and then it's got a flat spot on the back side, on the bottom side, I should say, and that's the negative. So this side would be the positive, and this side would be the negative on that. And in fact, the battery is nominally 1.5 volts. But if you actually test it the day you buy it, say, and no current's coming out of it, you might get around 1.68 volts, or maybe up to 1.71 volts. Okay. And that's sort of the EMF of the battery. And they use this symbol for that. Okay. We also model a real battery. So this battery is these 2 that I've drawn. They're just basically ideal batteries. They're batteries whose voltage stays, if I say it's 12 volt, it's going to stay 12 volt, period. But in reality, it doesn't. Real batteries don't do that. Real batteries actually reduce their terminal voltage when current's being drawn through it, and eventually they reduce it so much that it's no longer useful, and that's when the battery's dead or needs recharging. So it turns out, if you want to really model a battery, what you do is take this diagram that we have here and then put a short bar and a long bar in it like that. and that's what's inside. But then you run into a resistor like this, and that's your internal resistance. Whereas this quantity is your electromotive force. So we can now say that V terminal, once you figure out how much current the whole circuit's actually using, then you'd find out that V terminal is equal to the EMF that you treated as the ideal battery minus the current it's drawing times that internal resistance. So basically, if you saw that an amount of current I is going out of that, and of course coming into that, like that, then you'd know this is the terminal voltage. Okay. And we even picture this internal resistance as going, up over time. It's not unlikely or not aberrant to use the internal resistance to be like half an ohm or a single ohm, something like that. But if you wanted to really represent a battery as it's dying, you might have to push that up to 2 ohms or 3 ohms or something like that. So that's really how we deal with batteries. The important thing to remember, and your book talks about this, it's kind of good. It talks about how you actually connect a battery to make a circuit, and you've luckily had all these labs, so I'm thinking you feel pretty good about that. But it gave you a series of pictures of batteries with light bulbs and wanted you to try to show how you connect them or what ways would be acceptable. So let me show you the way that actually is acceptable. So we can say this is our battery right here. And right here is the positive part. What we can do in principle is we can take, let's say, the bottom of the light bulb, which has a little nub down at the very bottom, and that material is usually lead. Like you can solder it. I mean, you can just put a soldering iron on it and it'll melt almost instantly. Then it has an insulator between that lead and the metal that the threads have. So now you come out here and you say, well, all right, well, this is the metal casing for the light bulb, and it goes up like this. And there's another thread, say there. And then your light bulb would be, let's just say like this. Obviously, I ran out of room. Let's undo that. What I'm going to do is this. Pick this baby up. Put it down here. Put it right here. That's probably good enough. All right. Now that I've had that, I'm going to take the light bulb and it's going to come out here like this and be something like that. Now, what you're going to notice is inside there's a wire connecting somehow to the threads, and it's going to come up and spiral around like this, and then come up and touch the lead down in the bottom. So that's why me having the lead on the positive point there is cool, because it's where the current can leave the battery and go in through the bottom. But you also need the wire to be able to return the current. You can picture it, even though it's not really happening that much. You can picture it as if the battery is pushing positive charges out of its positive end. They're going through all the circuit and then returning in the negative end. So if you don't have that wire to return it to the negative end, it's not connected properly. So what you do now is you take another wire. I'm using blue for the metals, obviously. I'm going to take this wire and attach it right here by saying soldering or something like that. And I'm going to take that wire and just let it touch the bottom of the battery, as we see there. And that is correctly connected. So anything that doesn't have one part of the battery touching the threads and the other end of the battery touching or being connected through a metal to the bottom of the bulb is not correctly set up. Anybody have any questions on that? So this is the case, this 1.5 nominal battery, that's actually the case for AA batteries, AAA batteries, C batteries, and D batteries as well. Obviously, it's not for the 9-volt batteries because oddly enough, they're 9 volts, but that's basically how all of them work. They're always 1.5 volts. A lot of times you'll have a remote control or toy or something that you need 2 batteries for, and you can, in principle, connect the 2 batteries such that the one battery has the negative down and the little positive nipple up, and then the other battery, the negative part touches the positive nipple of the other one, and then the positive nipple on top is connected to metal, and that goes into the motor or whatever part of the toy that needs the electricity, and then the wire comes back out and touches the bottom of the first battery. That's how you get a 3-volt power source. If you stack them on top of each other like that, and then added a third one, you get a 4.5-volt battery power source. Or if you did 4 in a row, or even 2 side by side, but just connected the head of the leftmost top battery to the tail of the rightmost bottom battery, and then ran off the topmost right battery, then you get a net of 6 volts. And of course, you could do 9 volts by having 3 rows, so on and so forth. So that's really how a lot of stuff's done, and that's actually how they're made too. So if you've ever seen some of these weird batteries, they sell it like Batteries Plus and stuff like that, like the one I have for that cross trainer back there. It looked really weird. It was like this big, and it was about that wide and about that tall. But I opened it up, and inside were basically just a bunch of D batteries. So they were all stacked up and wired together. So evidently the manufacturers, which mostly take place in China from what I understand, and some other countries, but most of those seem to be made in very specific increments. They're almost always 1.5 volts, 3 volts, 6 volts, 9 volts, 12 volts. And a lot of times even those 6, 9, and 12 volts are just 3 volts stacked up or 1.5 volts stacked up. So that's just something to know. It's also kind of not unreasonable if you took 2 batteries, instead of sticking them on top of each other, like here's the positive end of a AA, here's the negative end of a AA, and you take a AA and stick it on top like that. That's the stacking them on top way that we were talking about. Here's the positive end of the top one, here's the negative end, but they're doing that makes it 3 volts. But you could also, instead, if you needed only 1.5 volts, you could put them side by side and then connect the 2 positives and the 2 negatives and drive a power source that way. That still gives you just 1.5 volts. So you'd have to have a 1.5 volt motor or whatever that you're running, something that only needed 1.5 volts. But what you're doing now is you're getting the 1.5 volts you need, but basically the battery is supplying, each battery is only supplying half the current, so it'll last twice as long. You could actually put 4 side by side and make it last 4 times as long, stuff like that. So you can do it that way, and you don't have to just do it one. You could do 2 stacked on top of each other, so that's 3 volts, and then another 3 volts next to it, and then another 3 volts next to it. Connect all the positives, connect all the negatives, take the negative and stick it to one end of the motor and the positive the other end. Then you have basically 3-volt power source with 3 different battery setups running it. So it's going to last basically 3 times as long. Does everybody follow that? I hate just talking to you guys. I like it better when y'all have questions. So I at least can figure out that whether you are understanding or tracking or whatever. So feel free to speak up or type up. I just put out my chat window again so I can make sure I keep track of that. All right. So with that in mind, and that history, like I said, that history of the development of electricity and magnetism is super interesting anyways. So I highly recommend any books you can find on James Clerk Maxwell. That's James. It's Clark, but it's British, so they spell things a little funny. Whoa, and evidently they erase things here in America. Maxwell. So if you find any books on him, that's pretty interesting read. You can also find books on Oliver Heaviside. And Michael Faraday. You can actually find a lot of free books by Michael Faraday in electronic format as well. And some of them, he has some autobiographical ones as well. So those are good. Heinrich Hertz is another one. I'm pretty sure his first name was Heinrich. Heinrich Hertz. All of these people were really making up this stuff. So you got Volta, you got Galvani, you got Cavendish, basically a lot of different people all involved, but all of those people were involved with the making of this. And the electricity and magnetism came out in 4 equations called Maxwell's equations. And basically what Maxwell, by his own admission, was basically he got the Lucasian chair of mathematics at Cambridge, and he was given access to Michael Faraday's experimental books, and is basically all of his output from his experiments he ran. And he said all he had to do was pretty much just write them down and translate them into mathematics. Faraday had done the lion's share of the work, and he only had really, between the stuff he did, which was in some cases just mimicking and confirming what others had done, but in other cases it was real discovery that he made on his own. Between that stuff and all the stuff that he had recorded for other people, Maxwell was able to write the 4 equations that we know of as Maxwell's equations. But he also saw an internal inconsistency of one of them and corrected it by adding a term to it, and that made quite a big difference. So anyways, it was ultimately published by Maxwell, but Maxwell used electric potential and some pretty esoteric things. By today's standards, they're very esoteric, but even by those standards, they were not what was being used. This was a big time where we were actually trying to send electricity from Great Britain to the Americas. And there was a big industry of running cable under the ocean to Nova Scotia and other parts of Canada, and then on to America. And people were learning electricity and magnetism on the fly by doing this underwater sea thing. And therefore, they had moved on and started using other types of mathematics and other quantities that Maxwell was not necessarily familiar with. So he wrote it in terms of these potential things, which again, like I said, nobody used then or now. But he also wrote them in quaternion form, which no one knew except for Hamilton, who died shortly thereafter and thought that was his greatest discovery. Though Hamilton we know of from a lot of branches of mathematics, none of which were about his quaternion stuff, even though we do learn them as physicists, and I'm sure mathematicians learn them as well. So anyways, that all became Maxwell's equations, and it turns out that other than some fairly obscure things that you would need relativity for to explain about electricity and magnetism, the Maxwell's equations are good to go. The one thing that Maxwell's equations are absolutely good with is special relativity, because in fact, that was the inspiration for Einstein. He was looking at Maxwell's equations, putting them together, making a wave equation, and then the wave equation, from it was obvious that if you replaced one reference frame that you were sitting in with another reference frame that was moving with respect to you, there was nothing that changed about the wave equation. So he made the conclusion that the speed of light is a constant independent of the motion of the source and independent of the motion of the observer. And that's because electricity and magnetism were telling him that already. And the only way he could make sense of the world without a lot of weird paradoxes was to assume that that was the case. And that was 1/2 of the principles of special relativity that he ultimately published in 1905. But it's kind of neat to know that it's actually relativistically correct. So that's cool. Your book shows, for instance, as a battery, it has a carbon electrode, which tends to become positive, and a zinc electrode, which, again, when I say tends to become positive, I mean with respect to the metal that's currently in. So for instance, in this case, we got the 2 metals are carbon and zinc. Zinc becomes, and I know carbon's not exactly a metal, but I think you understand what I mean. It is a conductor to some extent. but the zinc is the one to actually likely collect electrons, and the carbon is the one likely to give up electrons. And if you take those two rods and submerge, them halfway up in sulfuric acid, then you have a battery. And that was that would be an acidic battery. Of course, you're used to hearing alkaline batteries, so you'd want to use some solution other than sulfuric acid, maybe a sodium hydroxide solution like lye or something like that. So anyways, your book does show that. It shows the different ways that you can connect a battery. It also shows how a light bulb is wired and what parts you connect it to. It does talk about electric cars. I'm not going to cover that. There is some very interesting stuff in it, and it's amazing how much acceleration cars can get, electric cars can get, given my familiarity with electric motors being from like golf carts. You feel they got a little bit of takeoff, but that's about it. But the Tesla literally 0 to 60 in 1.9 seconds is pretty amazing. And there's some that are even better. So let's talk about current now. So if you want an idea of what current is, I've sort of already told you guys when we did our Ohm's Law lab, a little bit when we did our electric field mapping lab, because remember, we found lines of equipotential. So in retrospect, from where you are now, you understand that equipotential means each one of those lines where all the points were connected, every point on that one line had the exact same voltage as all the other points on that one line. And then if you move over to another equipotential line, that one had a different voltage, but that whole line had that same voltage, and you keep on doing that. And in fact, if you, at least on a small scale, measure the change in voltage from one line of equipotential to another, and then you divide that by the distance of separation, you'll get the actual magnitude of the electric field, at least at that point. Okay, so that's something very important. But it was those difference in voltages, according to Ohm's law, that actually creates a current. Ohm's law says that V is equal to IR. I'll write that here. And what that means, if V equals 0, then I equals 0. Okay. So if you don't have a voltage difference between the ends of two things, or of one thing, I should say, like a wire, if you have a voltage difference from one end of the wire to the next, and the voltage difference is 0, no current's going to flow across it. No ifs, ands, or buts about it. I've used a lot of arguments making the claim that the wire is a surface of equipotential, and it sort of is, but in reality, even the largest area, so that more stuff can fit through it, and the shortest lengths of wire still have some resistance. So if you connect, even a wire that's as big around as the little bump or nipple or whatever on the positive side of the AA battery, if you connect that wire that big straight back to well, let's just leave it there, and then say it's going to go to a resistor, and then it's going to go from a wire just like that one from the resistor to the negative side. What you would find out is right at where the battery touches that wire, that voltage will be V terminal. It'll be the terminal voltage of the battery. So probably, let's say 1.5 just for ease. Well, by the time it gets to that first resistor, it might be so close to 1.5 that our meters can't detect it. But to be honest with you, it's probably more like 1.49999 or something. So even, with really nice metal like copper, or even if you use silver, which is really among the best, if not the best, it's definitely the best element to use for wire, but it's kind of expensive. But even with silver, you're still going to have some resistance across that. Therefore, there's going to be a little voltage drop. Therefore, there's going to be current running through it. Okay. So what is the current? Well, if you imagine in a circuit, so let's picture this circuit right here. Imagine you have a circuit, and the circuit goes up, comes around here, runs into a battery, or excuse me, a resistor, like that, and then goes around here and then comes back to the battery. That would be your circuit. Now, if you just imagined a little line right here, okay, and then you watched there, okay, like that, you could sit there and count electrons. And actually, you could pretend to be counting positive particles because the electrons would actually be moving to the right there at the red line, whereas the positive particles that don't exist would actually be moving to the left. But if you could imagine picturing those charges going by and you count them, going by, and I'll say that the charges that you count is delta, I'll just say it's N. Okay, so that's N charges going by, and they're going by in a time delta T. Then the current, I, at least on average, is N times Q per N divided by delta T. In other words, think of electrons. For electrons, the Q over N magnitude is 1.602 times 10 to the negative 19th coulombs. Okay, so that's what current is. It's really the amount of charge passing a point in the circuit divided by the amount of time it took. Or you could just say, I'm only going to time it for 1 second. And then you're going to take the number of electrons you saw moving to the right and say the current's moving to the left. And the amount of current is the number of electrons you saw times 1.602 times 10 to the negative 19th divided by 1 second. And that gives you the ampere. So we end up getting, in fact, if we didn't want to take the average, we'd say I is equal to dq dt. So that's one way of looking at it. And this is another way of looking at it for the average. Or you can go a little further and start thinking about the unit. So to do that, you would think, okay, well, I is defined to be coulombs per time. So that must be, charge per time, that must be coulombs per second. And the coulomb per second is defined to be the ampere. That's another name I could have put on the biography list on the previous page. But ampere is abbreviated with a capital A as well. So amperes mean coulombs per second. And for instance, you could say, here's an example. If 3.5 amps exists in a wire for, let's say, I'm actually trying to make an example just like the books. I'm just making up numbers though. So 3.5 amps exists in a wire for, let's say, 5.0 minutes. Then how much charge passes a point in that 5.0 minutes. So that'll be part A. And then part B, how many electrons would that be? Because we know electrons are really what's doing the moving. But in this case, the electrons obviously move the opposite way of what we say current moves. And we'll talk a little bit later about when that's a problem. And there's really only one time that's a problem. But since there are electrons moving, if you know the total charge and you know the charge per electron, you should be able to figure out the number of electrons. So here's our solution. Anybody have any questions on the problem? I feel like I'm talking at you guys. I'm sorry. So we have I, at least on average, is delta Q over delta T, which is another way of writing N times Q over N. So anyways, you can use this one as well. So I'll go ahead and circle it just to make sure y'all know this is one of those equations you can use. Put a bar over it. It's the same as the first equation with the red box on it. But anyways, from that, we can see that delta Q is equal to I bar times delta T. And they didn't even say the current was changing. So really I bar is just going to be plain I in this case. So it's going to be 3.5 amps, which remember is a coulomb per second, times 5 minutes. What 5 times 6 is 30. So 5 times 60 is 300. So that'd be 300 seconds. And again, remember we told you that that amps is coulombs per second. So when I multiply that by seconds, I just get coulombs. So the answer is 3.5 times 300 equals 1050 coulombs. Okay. So that's the answer for part A. That's a lot of coulombs. Remember, I told you it's not unreasonable to expect a lightning bolt to only deliver maybe 100 or so coulombs of charge. Now, this is a substantial current, 2.5 amps. It only takes a milliamp to kill you. So 2.5 amps is a buttload of current. And it's for a long time. It's for 5 minutes. Actually, 3.5 amps is what I said. So now if we do part B, we can go ahead and see how many electrons that'd be. But the main thing I was saying is, yeah, that's a lot of electrons being delivered by whatever power source that was. So let's do part B. And for part B, I'm going to say E, the charge of the electron, is equal to 1.602 times 10 to the negative 19th coulombs. And sometimes it's helpful to take numbers like this and write it per electron, because there's some ambiguity when you first try to solve a problem and you've got two numbers and you don't really have an equation that would relate the two numbers. Sometimes you can just use dimensional analysis to figure out what to do with the numbers. So the numbers we have are E is equal to technically negative 1.602 times 10 to the negative 19th, but we only care about the magnitude. And we also have delta Q is equal to 1050 coulombs. So you see, if I multiplied E times delta Q, I'd get coulomb squared per electron. That's not helpful. If I divided E by 1050 coulombs, the coulombs would cancel out and I'd just get some number per electron. So that's not good. So ultimately, you might finally think, well, let's divide the delta Q by the E. And that's what I'm going to do. So I'm going to say delta Q divided by E is equal to 1050 coulombs divided by 1.602 times 10 to the negative 19th coulombs per electron. Now you see what happens with these units is division is the same thing as multiplication by the reciprocal. So I'll take the coulomb that's on top, and now I'm going to multiply that by E minuses per coulomb, and you see that you only get E minuses. So that's a second confirmation of how the units helped us. So I'll take this 1050 and I divide it by 1.602 e to the negative 19, and that gives me 6.55 times 10 to the 21. I'll say this is equal to the number of E minuses. And I wrote it in blue, so I'll box it off in red and say this is the answer for B. Any questions on that? Okay, another thing you might see, You've probably seen portable cell phone chargers at Walmart and stuff like that. And a typical one that I've seen is a portable charger advertises 100,000 amp hours. What is that? Okay, well, here's the solution. Since 1 ampere is equal to 1 coulomb per second, and 1 hour is equal to 3,600 seconds, then the number of amps times the number of hours equals amount of charge. So the amp hours is really a number of coulombs in some sense. Okay. And in fact, you can see that 100,000, well, actually we say, let's do this instead. I'm going to do 1 amp hour. Dang it. So 1 amp hour would equal 3,600 coulombs, and 100,000 amp hours would be equal to 1 times 10 to the 5th coulombs per second times 3,600 seconds, which you can say is 3.6 times 10 to the third is what 3,600 is. And then you could say 3.6 times 10 to the 8th is the total number of coulombs that you get in 100,000 amp hours. So as I told you, you can sort of picture, even though it's not necessarily exactly what's going on, you can sort of picture like a battery as this little fountain where positive charges are shooting out the positive side of the battery, and then they are returned in through the negative side. So when you say, hey, I've got a charger that has 3.6 times 10 to the 8th coulombs, or 360 million coulombs in it, then you can connect that to your battery and think, oh, okay, so if I charge this thing all the way up, it starts with 360 million coulombs. And then if it says it's now only 95% charged after it filled my phone, then evidently 5% of 360 million is about how many coulombs of charge my battery holds. So that's kind of a nice way of thinking about it. It gives you some at least ballpark figures of what you can expect on charging times and stuff like that. Now, I did mention to you that there's exactly one time where the conventional current not being real could actually cause problems. So let me show you what that is real quick. I want you to imagine a wire, and this is called the Hall effect. So we're going to draw a wire like so. And what we're going to do is we're going to immerse this wire in a uniform magnetic field. Good, dude. Okay. And let's say these little diagrams like this are supposed to represent the back of a vector, or the back of like an arrow from a bow and arrow. So you're looking at the little feathers on the end of the bow and arrow here. Whereas if you saw a circle with a dot in the middle, you're looking at the actual head of the arrow. So that's what that means. And that's supposed to be a magnetic field. Now, magnetic fields act in weird ways on charged particles. For starters, they only act on charged particles if the charged particles have any velocity. So if we're saying a current I is going this way, there's two ways that happens. Either a positive charge is going this way, or a negative charge is going this way. Okay. Well, it seems that the force that a charge feels is equal to Q times V. That's the charge times the velocity, the cross product of that with B. So we see the B, our vectors pointing into the page, the V for the positive charge is to the right, the V for the negative charge is to the left. Now, if the left is really what happens, then what's going to happen is QV points to the right and B points into the page. So I can use my right hand like this. And what that means is the vector QV is my index finger. So that's the direction that Q times V is pointing. And remember, if the charge is positive, then it's not going to change the direction of the velocity at all. But if the charge is negative, it's going to change the direction of the velocity by 180 degrees. So you take QV and point your index finger in that direction. You hold your middle finger like it's a trigger finger, if you will, and the index finger being one that would be going alongside the barrel if you're holding a gun. But the main thing is this finger pointing to the side here, that's going to represent the magnetic field. And then your thumb on your right hand, again, it points in the direction of the force. And all three of these are supposed to be mutually perpendicular. So your hand should be ideally where your thumb's perpendicular to your index finger and perpendicular to your middle finger and all that stuff. So if I do that with this case, the positive particles going to the right, the magnetic field is actually going into the board. So you see the force is up. And what that's going to cause is basically the positive particles are going to all end up on the top side of this wire. Okay. Now, if on the other hand, if it's a negative charge, now the V is this way, the V is this way, but QV, since Q is negative, is that way. So again, you have a force that points up. So in this case, what you'd have is a negative particle would go there, another negative particle would go there, another negative particle would go there, another negative particle go there. So you'd have one of these two results. So with the red case, it would be this, and with the blue case, it would be. And therefore, if you took, for instance, let's draw our multimeter. Oops. Sure. No, well, I'll leave it be. I've got that set to volts DC. I've got the screen reading here. I'm going to say this is the black COM, and this is the red V omega. So what I would want to do is take this and connect it to this side of the wire, and then take this and connect it to that side of the wire. And when you do that experimentally, the result you get is negative 0.079 volts. What that means is, in fact, it's the negatives that are moving, because this top part of the wire would have a lower voltage than the bottom part of the wire, and it's more like the negative plate of the capacitor, and the bottom's more like the positive plate of the capacitor. So that's called the Hall effect. And unless you're dealing with a magnetic field in that a current carrying wire is in, and you actually need to measure the voltage difference from the top to the bottom of the wire, then you're not going to notice the difference between whether it's negative particles moving to the left or positive particles moving to the right. Does that make sense to everyone? I'm not saying it's super easy. I'm just saying it should, in some sense, make sense. So we've talked about a few things. This is an equation, by the way, this F equals QV cross B. We're not using that in this chapter, but we'll be doing so soon. But you can already start thinking about it if you want to start thinking about how magnetic fields affect charges that have a velocity. Then you can use that. I did mention, no, I did not. That's right, because we haven't covered magnetic fields yet. By the way, the unit for the magnetic field is called the Tesla. That's the unit we have to use in our equations. So this guy right here means B is equal to the Tesla. You'll also notice that it's a Newton per amp meter. And you'll also notice there's another quantity called a Weber per square meter. And there's another quantity called a Gauss. And then there's another quantity, which is the one we use, is the Tesla. And sorry, this equals was not supposed to be there. So this is 1 Newton per amp meter. Those are various different ways. What I need you to know is B for the Earth is about, this is the magnetic field of the Earth, is about 0.5 Gauss, which equals about 0.5 times 10 to the negative 4th Tesla, because 1 Gauss equals 10 to the negative 4th Tesla, or 1 Tesla equals 10 to the 4th Gauss. Tesla is on the order of an MRI's magnetic field. So if you have ever had an MRI, that's around the magnetic field strength. It can be a little bit less than a Tesla, it can be a little bit bigger than a Tesla. I think they actually have different power ones. I'm not really sure, but I know when I asked, when I had mine, one time when I had mine, they told me it was about a Tesla. Or sometimes they'll say it's 10,000 Gauss, and that's sort of the same thing. So anyways, that's just some extra stuff to cover. I've already covered Ohm's law. And what I want you to understand about Ohm's law is looked at in a couple different ways. You can say, for instance, like you did in lab, you can make a voltage versus current plot. So here's current on the horizontal axis, and here's voltage on the vertical axis. And you could get a string of points like that, which would result in a line of best fit like that. And in that case, M equals slope equals rise over run, and that's equal to R, the resistance. So this is, if the graph looked like this, they would call this an ohmic device, because it appears to have a constant resistance. And therefore it looks just like what Ohm's law said. And I accidentally chopped off part of my R there and part of my E. That's good. Okay, so it's an ohmic device. But as you saw, for instance, with a light bulb, that's not necessarily the only thing. You can have graphs that look like this, in which case this is a non-ohmic device. Like a light bulb. And the reason why this one had a low slope at the bottom, at the lower left-hand side, and a higher slope at the right-hand side was the higher the current you put through it, the hotter it got. And the hotter it got, the higher the resistance got. And that's exactly the way you want tungsten or a tungsten filament in a light bulb to behave. Because once it gets up to a certain temperature, it becomes visible, and that's the light we're shooting for. Of course, all the time before that, it was producing heat in the room, which if you're in the summertime, you're not very happy with. So that's just something to keep in mind. So that's one way of looking at Ohm's law, is that there exist certain things that are called ohmic, and the slope of their graph will be in fact a straight line. The graph itself will be a straight line, and the slope will be a constant, and that's for ohmic devices. But another way of looking at V equals IR, it says a voltage drop produces a current I, and the factor between them is called resistance. And I'll just say R is measured in ohms. Okay, so that's called Ohm's law, which again, y'all have already had a lab on this, so you should know it, but just in case, this is Ohm's law. And in this way of saying it, what I'm saying is, if there's a voltage drop across a thing, meaning one side has a higher voltage than the other side, then the change in that voltage, V, is equal to the current going through it times some constant, at least for that particular voltage and current. When you get that particular voltage and current, and if you take the voltage and divide it by the current, you'll get the resistance. And now if that device is ohmic or not, that's going to be considered to be the resistance period. But you might actually have a graph that looks like the red one, in which case the R is not going to be constant. So if you find another I, you'll find a different V associated with it, and that V will be, or that R will be given by that V divided by that I. So that's a couple ways of thinking of it. The other thing that's actually very important for us is to know about power. And this is one of the things I tell my students is really good to know from a standpoint of if you're ever going to be, let's say a grown-up that maybe owns a house or has a lawn to take care of, or, starts doing odd and end jobs and stuff like that with electricity. Well, then it's really useful to know this equation right here. And the equation is, your book derives it, by the way. I don't see any need to, but the one formula that you use is P equals IV. I know you guys, being calculus-based physics students, are not algebraically challenged, but in case you get into the stress of it, sometimes rewriting equations like Ohm's law and this power equation this way can be very handy. So you take the one thing that's on the side of the equal sign all by itself, and you put it up on top, and then you count the number of things that are on the other side by side, and you make that many spaces down in the bottom. So this one only has two, I and R, so I'll leave two spaces, and I'll put I here and R here. And again, I wrote it in the wrong color. So I, R. You can see if you want to solve for R, you cover up the R, and it looks like V is being divided by I. That's right. That's the mathematical operation you do. If you want to find the current, you cover up the I, and that looks like V divided by R. That's what you do. And finally, if you want to know the voltage, you cover up the V, and it looks like I times R, and that's what you do as well. Similarly, you can say, make a similar circle for the power equation. Well, I got in my own way and my circle went really badly. So that is a beautiful circle. And this one also has only two terms. So what I'm going to do now is I'm going to say P is on top, I is here, and V is here. So again, that little circle will help you. If you need to solve for I, you can cover up the I, and that says divide the power by the voltage. If you want to solve for the voltage, you cover it up, and that says divide the power by the current. If you want the power, you cover it up, and you multiply current times the voltage. Now, this is part that's really important as well. So what if you know I and R, but not V? Well, you can take that same equation, the P equals IV, and you can use Ohm's law, V equals IR, and replace the V with IR, and you'll get I squared R. Also, if instead you knew the V and the R, how could you calculate the power then? Well, you could take Ohm's law and solve it for I and replace the I in P equals IV with that. So I is supposed to be V over R. So another result you get is V squared over R. Now, all of these are correct equations, but this middle version is particularly important because this middle version is the reason power lines through big open fields So the reason power lines through big open fields are often at 100,000 to 2 million volts. Okay. The reason is, let's say your power source, your electricity generating facility. So this is generating facility. So this could be, for instance, a coal-fired power plant that basically uses steam turbines to turn it into electricity. Let's say the wire comes out at, V equals, let's say 125 volts. And it's actually AC, which we haven't talked about, but I'm telling you, I'm using all the equations that are still okay, even in AC. Now that power line is going to go from here up to those tall towers, which you're used to seeing. They look sort of like this. And they go ding, 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 like that. Okay. Well, there's going to be a voltage drop from here to the other end. There's just going to be a voltage drop, and there's nothing you can do about that. That's because the wire has a certain length, has a certain size, and so on and so forth. It's going to have a certain resistance. That means the voltage, which if you took it in, it might have been 125 volts, but here it might get to 120 volts because of the resistance. And then this would go to another facility that could change it around, and then that would go to a neighborhood. And I did not leave enough room. So I'm going to kill that. But anyways, this would be like a typical neighborhood. A typical neighborhood, of course, has hundreds of houses, and each house uses 200 amps. So let's say area with 1,000 houses at 200 amps per house. Okay. So no matter what, the current that this power supply is going to have to deliver is 200 times 1,000. That's 200,000 amps have to come in. Well, according to this formula, that means you're going to take 200,000 and square it and then multiply it by that itty bitty resistance of that wire. And that's how much energy you're just going to waste to heating up the atmosphere. Just because the current's going through there, it's going to generate heat and those wires will physically get hot. That heat will be extracted from the wires to warm up the air around it, which you didn't necessarily want. And all of that money is wasted. In other words, that's electricity they can't sell. So it turns out if instead, let's say you come out here and do a step up transformer, from V equals 125 volts to 1.25 million volts. Okay. So this is 10 to the fourth. This one's 10 to the sixth. So, actually, this one's 10 to the two. This one's 10 to the sixth. So it's 10 to the four. So it's a times 10 to the fourth transformer. So what's going to happen now is this wire is going to come up here and its voltage is going to be 1.25 times 10 to the 6 volts. And it's going to run the same way and then get back here and maybe it'll be 1.2499990 volts here. In other words, the resistance of the wire is not going to bring it down very much, just like it didn't with the 125. And now what you've done is you've increased the voltage by a factor of 10 to the fourth. So the current, now the current is equal to 200,000 amps divided by 10 to the fourth, which equals plane, that's 1, 2, 3, 4. Oh, I didn't draw enough zeros there. Hold on a second. That was supposed to be 200,000. That one should be amps. So when we do this now, we get basically 20 amps. So let's say R equals 5.0 ohms in both cases. Then what that means is V is equal to 20 amps. This is in the second case, 20 amps times 5.0 ohms, which gives me basically a voltage drop of 100 volts. But V1, we had 200,000 amps times 5.0 ohms, which is actually going to break it down quite a bit. Or excuse me, 200, yeah. So 2e to the fifth, I don't even know why I did that, times 5 is equal to 100. That's 1, 2, 3, 4, 5, 6. Yeah, that's a million. That's what I was thinking. That's going to be a 1 million volt drop. So that's kind of suboptimal anyways, but the main thing is now you can see that P equals I squared R saves a lot of money. And the reason why that 10 to the fourth was used in both increasing the voltage and decreasing the current is because the current times the voltage is the power. And if you've got a perfectly efficient transformer, the power that goes in should be the same as the power comes out. So if the voltage went up by a factor of 10,000, that means the current has to go down by a factor of 10,000. So that's why that became the case. Anybody have any questions on that? We're going to work more problems next time, but I'm going to go ahead and give you 2 more equations we need. This one should make some sense. The resistance a chunk of wire would have, if this is your chunk of wire, say, if this is the cross-sectional area A, and this is the length L, then we suspect the resistance should get larger with a longer length of wire. And we also expect the resistance should get smaller with a bigger area. That turns out to be right. And then all we need is a factor to make this an actual equation instead of a, related to. And we also need something to dictate what the material is, because of course, silver is a better conductor than copper, and copper is a better conductor than aluminum, and aluminum is a better conductor than gold. So we want something to indicate that. Well, that something is this, and it's called the resistivity. And the resistivity, of course, rho has units of ohms times meters. And I'll also tell you that 1 over rho is defined to be the conductivity. But they're all properties of materials. So your book has a table on them. And in fact, the unit for the for the conductivity is 1 over ohm meters, but that's defined to be, and I love this unit, it's defined to be the mho, M-H-O. All right, so that's 2 parameters that are helpful. And of course, we also have a new equation that's helpful that helps us determine the resistance of a piece of wire if we know its length, cross-sectional area, and resistivity, which we can get from a table. But there's also a temperature relationship that tells you rho at some temperature T is rho 0 at some temperature T0, then they are given by 1 plus alpha times T minus T0, like this. And this is called the temperature coefficient of resistivity. That's also given in that table. So you'll need these equations, but again, the values of these constants come from the tables, so you can look them up. You now have just about every equation you need to do stuff from this chapter. And I've sort of explained them, but I just haven't used any examples or showed you any examples that are that helpful. I will point out that in these power formulas, if we're talking about the power and going from the generating facility to the neighborhood, the I is the current going through it, and the V is the voltage drop across it, as I showed you down here in blue. The I squared R, I is the current going through it, but the R is the total resistance of that wire. And then V squared over R, again, that's the voltage drop in going from whatever it was when you left the transformer to whatever it was at the neighborhood where you're going to transform it again. That's what that V is. You take the difference between those, and then you divide it by the total resistance of the wire. All right, that's enough. And we just met the time crunch, so everybody's free to go. You can also stick around and ask me questions. I will be here if you need me. I'll wait for the last person to leave, but thanks for coming, everybody. You have a question, saying?
No, I'm just copying down the equations.
Okay, no problem. Actually, something I want to write down. I said it in words, but I didn't put it down here. Conventional current. You get it all saying? Anything else you need?
Yes, I got it.
All right. Well,
Uh,
have a good one,
thank
sir.
you.
You don't have any questions before we go? All
No,
right. Have a good one.
thank you. Bye.